So this is a truss where we're asked to find only certain member forces, the forces in J, I, C, and CD. Here's J, I, C, and CD. This, to me, implies that we're going to use the method of sections to rapidly find the information that we need without finding extraneous information, including things like support reactions or member forces in other members framing into other joints. Prior to solving for those forces, we want to first determine, is this a determinate and stable truss, and identify any zero force members. So the first step in the process would be to draw a free body diagram of the global system, and this just allows us to better understand the truss itself and identify any unknown forces that we're going to need to find and all geometry that we need. Since we have that truss right above this, I'm not going to add in the geometry to this diagram to keep it somewhat cleaner. But even if you have a problem where drawing the free body diagram seems kind of strange because we could just go ahead and add our support reactions to A and K there, the free body diagram gives us a little bit of a surety that we fully understand the problem. Just going through the exercise of drawing it, we see where all our forces are located, and we see what our entire geometry of the truss is. So it's really a valuable exercise, even if you think it's not really that useful in the final problem solving. The more complicated these trusses become, or any problem, the more important a free body diagram is. So I'm not going to add the 2 meter dimensions and the 5 meter vertical dimension there. What we know for this truss is that we would have two reactions at joint K. We would have a vertical reaction. We can call this RKY. And we would have a horizontal reaction, RKX. And I might as well go through here and label my joints as well. We have K, we have J, I, H, G, F, E, D, C, B, and A. Now at A we also have a pin support. Therefore at a pin we're going to have two unknowns, a reaction in the Y direction and a reaction in the X direction. So at this point we can say that we have the majority of the information on this truss. I suppose it doesn't hurt for us to put in a quick dimension here. 5 at 2 meters is equal to 10 meters, and a dimension vertically as well. Where we have 5 meters in the vertical direction. So now that the truss is fully identified and the free body diagram is drawn, we could start to identify the first parts of this problem. Is this truss determinate and stable? So let's first identify the number of members we have. B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 members. Now a member is something that spans between joints. So as long as the member ends at a joint, it's connected at that location, it doesn't skip that one, this is a member. A to B is a member. Even though A, B, C, D, E, and F are all collinear, there are separate members at each location. The number of reactions is R is 1, 2, 3, 4. And the number of joints, J, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now a joint includes the locations of the supports, and it includes where only one member terminates. So this one terminates at this support. It's only one member, but it's joined to the support. Once we have that, we can answer question A. The degree of static indeterminacy is equal to B plus R minus 2J for a truss. And this is equal to 18 plus 4 minus 2 times 11 is equal to 0. Since SI is equal to 0, we have a determinate. We have a determinate truss. And a determinate truss means that we can solve everything in this truss with only our equations of equilibrium. We don't need to bring in more advanced analysis techniques. Now, we'll note that if we were to want to solve this truss for reactions, we have 4 reactions and we only have 3 equations of equilibrium for a collinear truss, so, or a coplanar truss. So we have equations of equilibrium, and these equations, as we well know, are the sum of all forces in the x direction are equal to 0, the sum of forces in the y direction are equal to 0, and the sum of moments about any point on the xy plane, moments about the z-axis, are equal to 0. So with those 3 equations, we couldn't immediately solve for all 4 reactions, and we'll have to go into our structure, start working with the method of sections and joints if we were interested in the reactions. However, we can see that the problem doesn't call for those, so this was only an academic discussion. So at this point, we can move on to the second part and check our stability constraints. So for part B, is this stable? And I would say that constraint number 1, not all reactions are parallel and or concurrent. Alright, so let's just take another look at what that means here. We'll throw our free body diagram back up here. And if all of our reactions were parallel, if we didn't have, say, RAX and RKX, we only had the Y reactions, this would have an instability in the X direction, as a slight force in X would result in movement. And the same goes for if we didn't have let's say, the Y reactions, then it would be unstable in the Y direction. Now, all the reactions being concurrent, well, RAX and RAY intersect at one point, and RKX and RKY intersect at another point. So we don't have a concurrent reaction problem. And concurrent reactions means that we have a problem satisfying moment equilibrium. So that's check number 1, so we're okay with that. Now check number 2, well, we have SI is greater or equal to 0. And this just sort of verifies the same thing. We have at least 3 supports here, and that are 3 reactions, and that means that we are properly supported in that regards. And then the final check would be no internal collapse. No internal collapse mechanism. And here, this is something that comes with some experience, but if we look at the truss itself, we can see that everything is arranged in triangular simple truss elements. And this allows for us to say that nothing is going to form a collapsing hinge mechanism inside of it, like a rectangular arrangement of elements might. So, therefore, we can say stable. And this means that we can continue on with our analysis. So, if we look at problem C here, and we're asked for 0 force members. So, we can say that we have 2 conditions for 0 force members. We have case 1, which we just named case 1 for this class. We have 2 members framing into a joint. So let's say we have A somewhere over there, B somewhere over there, and joint C here. And there's no external force at that joint, and there's no reaction at that joint, and the members themselves are not collinear. In other words, they come in at some angle. Then we can say that A, C, and AB are both 0 force members. And if we have case 2, we have, in this case, we have exactly 3 members framing into the same joint, and 2 of which are collinear. Let's give A, B, C, and D. We have 2 collinear members, so AB and BC are on the same line, and BD is non-collinear to those 2 members. There's no external support or force at that location, then we can say the non-collinear member is 0 force. Those are our 2 cases. So for us, let's just make a quick table here, and let's say that joint, and then member, and then case. And for this problem, there's not too much to choose from, but let's go back to our drawing here. And if we look here, we're looking for a case with case 1 or case 2. Well, everywhere that could be case 1, F and A, where only 2 members frame in, either have an external load or support, so we don't have any case 1 conditions. Case 2, we're looking for 3 members framing into the same joint, so we have 2 possibilities. And the 3 members must contain 2 collinear ones, AB and BC, or HG and GF, 1 non-collinear, BJ and GE, and no external support or force. So here we have an external force, so that limits G, that makes GE non-zero force. But at joint B, we can see we satisfy all these constraints. So now we can identify member BJ, we note of joint B, as 0 force member. So at joint B, we have member BJ, and we have case 2. So at this point, we're ready to continue our problem and start to look for our forces. So we're going to find forces in JI, IC, and CD. Now to do this, we're going to need to identify first the locations of those members. So we can sort of highlight them here, JI. And then we have IC and CD. And with the method of sections, we're allowed to pass section cuts anywhere we choose. The goal of this is to, as quickly as possible, solve for all of the missing or values that we want to find. So here we're only after 3 member forces, and if we have 3 unknowns, we have 3 equations of equilibrium, we can solve it immediately. So let's give ourselves locations AA, and we'll pass a cut, as shown here, through the members that we don't know. And this exposes 3 member forces, and since we have 3 equations, we can directly solve for this. So we will cut through JI, IC, and CD on path AA. And then we will draw our free body diagram. Now, if we look at this cut, we have 2 sides to a cut, of course. We cut it in half, we get 2 halves. We have the one on the left, where we'll have a force, and a force that are unknown to us, and 4 reactions. And whereas the one on the right will have only 3 unknown forces and no reactions. It makes sense that we'll take the section on the right and put that into equilibrium to solve for our unknown forces. So let's draw a free body diagram of right hand side. And now we can simply draw the right hand side of that. So we're going over 6 meters. And we're going down to here. Oh, I went a little bit too far on that. Let's just erase some of that. And we will come up there. And yes, this will work. Okay, so at this point we have cut through a member here, and we have cut through a member there. So we've cut through this, and this member. That's why they're drawn as dashed lines. And let's give ourselves some joint identification here. I, H, G, F, E, D. Over here, where these two intersect, we have joint C. And somewhere over here, we've got joint J. So we have some unknown values here. We have an unknown force Fij. We have an unknown force here Fic, and we have an unknown force coming out of joint D that has a value, or that is FDC. Now the thing about these forces, we've chosen to draw them all as tension forces, pulling apart the joint, the member acting in tension. And this is because tension is positive in our local coordinate system. And then if we draw that as positive in tension, and then put them into our equations of equilibrium using our positive global coordinate system, if it comes out as a positive value, that means that the force in the member is in tension. If it comes out as negative, it means the force in the member is in compression. Now before we continue on, let's finish this diagram here, and we can say that we have a force at joint I of 3 kilonewtons, a force at joint H of 3 kilonewtons, at joint G of 3 kilonewtons, and at joint F of 1.5 kilonewtons. We have some geometry that we might as well add to here. So we have 2 meters, 2 meters, 2 meters. And then we have a value here, let's call this the value between, or the distance between the top of the truss at joint I and the vertical component at joint C here. Let's call that H. And we can say that H over 5 meters is equal to 6 meters over 10 meters. So we're just taking a similar triangle of the entire truss versus this small segment of the truss, and we end up calculating H is equal to 3 meters. Now let's look at one other piece of information that we should identify before we go much further. And this is the force components in force DC. So we have FDCY and FDCX. Now they're drawn such that when we add them together, the vector sum of the two will add up to FDC. So let's make us a little space over here, and let's look at the relationship between FDCX, FDCY, and FDC. If we draw our components of that force over, we can see that we have force FDC, we have a force FDCY, and a force FDCX. FDCY itself has an angle to it, but we can express that as a slope. We can say for every one vertical rise we have 2 horizontal, and that puts us at root 5 in the diagonal. So if we go back to our original diagram here, we had 10 meter length, 5 meter height. So that's a ratio of 1 to 2, and the hypotenuse would be root of the sum of the squares. This means that now we can say FDCX is equal to FDC times 2 over root 5, and FDCY is equal to FDC times 1 over root 5. So at this point we can begin applying equilibrium conditions to our free body diagram. Now, where we begin with that depends on us using some strategy to analyze this. So we have this given free body diagram, and if we decide to take equilibrium, we can't take sum of forces in x and find our solution right away because we have 2 unknown x components. And we can't take it in y and find our solution right away because we have 2 unknown y components. However, if we strategically take equilibrium about a point, moment equilibrium about a point, we can reduce some of our unknowns. So I chose to take moment equilibrium about point C. Then we have FIC traversing through that point and FDC traversing through that point, along with this 3 kilonewton force here. So this means that our moment equilibrium equation will not contain these 2 unknown forces because their moment arm will be 0. So let's apply equilibrium, and we have 3 equations to work with. That means we can find 3 unknowns. So let's take sum of moments about C and set that equal to 0. And then if we do this with our positive sign convention, a positive Fij times 3 meters. So that'll be rotating it this way. There's Fij, it's rotating it counterclockwise about point C, minus 3 kilonewtons times 2 meters minus 3 times 4 meters, so that's rotating it clockwise, minus 1.5 times 6 meters is equal to 0. And then we can say that Fij is equal to plus 9 kilonewtons in tension. So we've directly solved for one of our 3 unknowns. And we're ready to move on to the other equilibrium conditions. So we can take the sum of forces in x and set that equal to 0. And this means that we have a negative force Ij minus FDCx is equal to 0. So they're negative because they're acting to the left. And if we plug in what we know, we have minus 9 minus 2 over root 5 FDC is equal to 0. And we end up with FDC is equal to minus 10.06 kilonewtons. That means, since it's negative, FDC is equal to 10.06 kilonewtons in compression. And we can put a box around that because that's one of our final answers. And then we have one further equilibrium condition, and that is the sum of the forces in the y direction is equal to 0. So if we add up all the forces in the y direction, we can say that minus FIC, so the force here, minus 3, minus 3, minus 3, minus 1.5, minus FDCY is equal to 0. And this gives us minus FIC minus 10.5 minus negative 10.06 times 1 over root 5 is equal to 0. And this gives us what value here? So if we move this out, we have minus FIC minus 10.5 plus 4.501 is equal to 0. Oh, I made a mistake there. Excuse me. So if we solve this, we have minus FIC minus 10.5 plus 10.06 divided by root 5, 4.499 is equal to 0. And this will give us FIC is equal to minus 5.55 kilonewtons. Since it came out to be negative, we can say that FIC is equal to 5.55 kilonewtons in compression. We can box that. And then the last step for us would be to draw our summary diagram. Our summary diagram will contain all of the known values that we've calculated for this truss and the given forces and support conditions. Since we never calculated reactions, we can't add those to the solution. Now, if we first go into this truss and we can say that we identified here was a zero force member, and then in force IJ was 10 kilonewtons in tension. So we can put in those little triangle arrows here telling us that we have a tension force, and this is 9 in tension. And force IC we just calculated was 5.55 in compression. So compression squeezes a member into itself. 5.55 in compression. And then we had a value of FDC of 10.06 in compression. So at this point we're done our summary diagram, and we've identified the magnitudes of all the forces and the directions of all the forces within the members that we were asked to, member IJ, IC, and CD. And since we weren't asked to do any other work for this problem, we can call it done. So I had made a slight error when I did this on the fly calculation. 10.05 plus, or negative 10.05 plus 4.499 is minus 6.0, not 5.55 I think I had. So now FIC is actually 6 kilonewtons in compression, and this changes our diagram slightly. We have 6.0 in compression on member FIC. The other members remain the same. It was simply a calculator error.